Good day everyone. In this video, we have been assigned to do a group presentation video regarding the subject KIB1015 Dynamics, which encaptures the analysis of prosthetic legs for amputees and also its relations to dynamics. Here are our group members.
Hi, my name is Imran, matrix number 22001200.
Hello, my name is Amir Shahmi and my matrix number is 220000911.
Hi, my name is KIB1015 and my matrix number is 22001121.
And my name is Muhammad Al-Rashid bin Anhar and my metric number is 23005038. So before we move on, let us overview of what are the contents that are going to be discussed in this video. First of all is the general introduction to what is prosthetic legs. Second is how does the dynamics and also its relations to prosthetic legs correlate to each other. Then we will be looking at the kinematic diagrams of the prosthetic legs. Then we will go to the analysis and also the calculations that are involved in the prosthetic legs. Furthermore, we are going to look at the materials of the prosthetic legs. Finally, we will be discussing on the future improvements that can be made onto the prosthetic legs. We will be looking at 4 features that are going to be our main focus in the prosthetic leg. One of which is in its durability. Prosthetic legs generally made of lightweight yet durable materials, which it can feature functional knee and ankle joints depending on the location of the amputation. Next is rehabilitation. Rehabilitation is a crucial part of the process which involves the physical therapy to strengthen the legs and learn to walk with the new limb, which involves the regaining of strength, endurance and coordination through targeted physiotherapy. Next is the distinct difference between the non-powered and the powered prosthetic legs. So for the non-powered prosthetic legs, which is also known as passive prosthetics, are designed to provide support and stability without any motorized assistance, while on the other hand, powered prosthetic legs are designed to provide additional support and assistance through motorized movement. Powered prosthetics are suitable for individuals who require more significant assistance during daily activities such as walking, running or climbing the stairs. But in our case, we will be focusing on the non-powered prosthetic legs. So how does the prosthetic legs correlate with dynamics? So, prosthetic legs are a remarkable intersection of engineering, biomechanics and also dynamics. Dynamics, which is the study of forces and motion, which plays a crucial role in the design and also the functionality of the prosthetic limbs. So there are 2 key points that are going to be discussed today, which is the force distribution and also the customization and the adaptability of the prosthetic legs, which we will be focusing on the lower limb prosthetics.
The graphic shows the dynamic analysis of a prosthetic leg with a 4-bar linkage mechanism. It depicts 2 postures of the prosthetic leg, illustrating the forces and moments acting on various components. A prosthetic leg's 4-bar linkage system is designed to imitate the natural motion of a human leg, allowing amputees to achieve a motion that is virtually identical to natural walking. This mechanism consists of 4 stiff links connected by joints that allow rotational motion, forming a closed-loop kinematic chain. The primary goal of this design is to build a functional and a steady prosthetic leg that moves naturally with the user's body. The function of the 4-bar linkage system is to transmit motion from the user's hip to the foot, mimicking the bending and extending actions of a genuine leg. The user's hip movement serves as an input motion for the thigh link. This movement is then communicated to the cuff links, which allow for the bending and extension of the knee joint exactly like an injured leg. Last but not least, the foot link offers a firm foundation and guarantees the prosthetic foot has correct ground effect. These forces and moments stabilize and control the prosthetic leg, allowing the user to walk naturally. Proper regulation of these dynamic interactions is crucial to the prosthetic's effectiveness, comfort, and safety. Next, the degree of freedom for this 4-bar linkage mechanism in this prosthetic leg is 1, which represents the independence of the motion driven by the user's hip movement. The number of links in this mechanism is 4, and the singular degree of freedom enables the mechanism to perform the intended motion of bending and extending the leg, mimicking the natural stride of a human leg. So to summarize, the 4-bar linkage of a prosthetic leg is a complicated mechanism that transforms the user's hip movement into coordinate thigh, calf and foot motions. This design closely resembles the natural motion of a human leg, resulting in a smooth and stable walk for the user. The dynamic study of the forces and moments operating on the prosthetic leg allows engineers to better understand and optimize its performance, resulting in a greater functionality and user experience. The 4-bar linkage system in a prosthetic leg is an efficient solution for people who need lower limb prosthesis because it properly balances the kinematic and dynamic elements.
Next, we are going to analyze and make some calculations for the prosthetic leg. 3 body diagrams would be done of the leg in one phase, which is the mid stance in the gait analysis. Then we will assume the parameters such as the mass of the legs and the mass of the device to calculate the forces and moments acting on the leg. Now the subject that we took on is only one subject. Sex is male, age of 23 years old, weight is 73 kg and height of 173.1 centimeters. Now, in order to calculate the forces acting on the standing leg, we would first observe the free body diagrams, and we would calculating the forces acting on the standing leg during mid stance. Now, based on this free body diagram, we can observe that we have 2 forces that we need to assume. First is the forces acting on the abductor muscle, and which is denoted as F. R is forces of socket of pelvis on the femur, and WL, which is the weight of the leg, and WB is weight of the subject, which is the 73 kg. Now, first we have to find the forces at point R, so we find the sublimation of Fx and Fy. Then, by using weight of leg, we can conclude that width of the leg is actually 60.68% of the weight of subject. So in this calculation, 16.68% times of 73 kg, we will get 12.17 kg, the weight of the leg. Then we would find the R forces. Next, we will find the moment at point R. R is the socket of pelvis on femur, and we would get the F, which is the forces acting on the abductor muscle, 58.08 Newton. Then find the X component of R, which is 19.86 Newton. Then the Y component of R, Ry, which is 651.32 Newton. Then we will get the total of R, which is 651.62 Newton, and we will find the torque at point R by using R is the pivot and finding torque, which concludes that we will get 6.97 kilonewton of torque at point R. Now the total forces acting on a standing leg is 58.08 Newton plus 651.62 Newton equals to the total forces acting on a standing leg would be the total of F plus R, which F is the forces acting on the abductor muscle and R would be the forces of socket of pelvis on femur, and we would get 709.7 Newton. Now this force would be the force acting on a standing leg, which holds our body, our upper body, and controls the stability of the whole body in mid stance, which is standing. Now it would take the same or larger force for prosthetic leg, as prosthetic leg would be more in mass rather than the actual leg to hold and stand the lower part of the body and also the upper part of the body.
So for materials, we only focus on two aspects, which are prosthetic sockets and also prosthetic body. For prosthetic sockets, there are two compartments that we would like to emphasize, which is the prosthetic sockets lining and also the prosthetic sockets shells. We consider two materials at first, which are urethane and also silicone. But after discussion and consideration of their characteristic, we choose urethane. And this is the reason why we choose urethane over silicone. The first one is urethane has a good biocompatibility, which reduces the skin irritation when in contact with the residual limb. And also urethane has high elasticity limits and a good shock absorber, which will enhance the comfort of the user during movement. And also urethane also is lighter than silicone, which can contribute to overall comfort when being used, and also increase the range of different genders and ages to use the prosthetic. And also urethane also less expensive than silicone, which make it more cost effective options, and it will increase the range of users no matter their income. So for the shell of the prosthetic sockets, we use carbon fiber reinforced polypropylene or CFRPP because of basically it is a better version of polypropylene, which it has a better strength and stiffness, and also better durability, and also a better dimensional stability. So for the dimensional stability, what I mean by dimensional stability is carbon fibers in the CFRPP will reduce shrinkage and warping during molding processes, which will increase the preciseness of the final product. While for normal polypropylene, it has a higher tendency to shrink and wrap during the molding process, which can affect the accuracy of the final product. Next, for the prosthetic legs bodies or the island or shanks of the prosthetic leg, there are many materials that are suitable as the prosthetic legs, but after comparing those materials, we choose aluminium. The first reason why we choose aluminium is because aluminium is significantly lighter than any other metals, such as stainless steel or even some composite. This will reduce the overall weight of the prosthetic leg, making it easier for user to move and reduce their fatigue. And the second reason is aluminium is reasonably strong despite being lightweight, and aluminium also offers a good balance of strength and durability despite being lighter than some metals. And aluminium also naturally forms a protective oxide layer, which will prevent corrosion and is corrosion resistant to many environment situations. Next is aluminium is generally more affordable than other high performance materials like titanium or carbon fiber, and this is a much more cost effective options rather than choosing carbon fiber or titanium as our pilot. And the last one is easy of manufacturing and customization. This is very important because in making prosthetic legs, we must customize the prosthetic legs according to the patient's conditions, their weight, their height, and also their ages and their daily activities. So by using materials that has a ease of manufacturing and customization, we can greatly reduce the cost and also increase the customize the prosthetic legs. There are some future improvements that can be applied in this current prosthetic legs model in order to increase its reliability in many aspects such as mobility, durability, strength, and its adaptability in various terrain and activities. One of the improvements that we can develop is the use of skin-like coverings that can be tailored to match the skin the skin tone of the user to make it more lifelike and discreet appearance. This type of coverings are made from durable, flexible materials that mimic the texture and color of natural skin, allowing the prosthetic legs to blend in seamlessly with the user's body. Next is the usage of modular design that incorporate easily replaceable modules, make it possible to do streamlined maintenance and repair in prosthetic legs. This approach allows prosthetists to swiftly address issues by replacing specific components such as joints or sockets. This will simplify the maintenance procedure and reduce the downtime for user, ensuring that repairs can be efficiently carried out with minimal disruption to daily activities. Additionally, these designs also enables prosthetic legs to be easily upgraded as new technology emerge. Next, we can also apply energy storage and return system in the prosthetic legs. So we can use carbon fiber springs, and it will be installed in the pylon or the shank of the prosthetic legs to further enhance overall shock absorption and energy return throughout the guide cycle.